is about geometry and graphs. So.
So first, there is an ongoing competition. I thought I was going to do better. I mean, who knows, Michael or Mickey, more time. And Tal, this was unfair what you did. I knew I was going to beat Avi, but actually I have some more support that my wife, Michal, and Nava Benor, had met even 2 years before Mickey and I met. They were in the same tent in basic training in the Israeli military, if you can imagine such a thing. No, officers course, sorry. So many good things were said about Michael. We've been actually in the last 10 years really next door neighbors in the university. But, not to repeat what other people said, and there is this word philosophy that we all like and appreciate, which means the love of wisdom. And I think, if I have to concentrate, he's a real philosopher in this respect. He really, you see the passion and you see the love of this and the dedication, and this is terrific. And he's in addition a wonderful citizen of the university and the department and so on, someone you can always come for advice, for help, nobody's willing to do this thing. Will you do this? And he says yes. So, it's great to have him as a colleague and friends. And okay, so this is for me what I'm going to tell you today, a part of a really big passion project, whatever you want. But I'll tell you some concrete things. I'm going to do business. It's not we're not here to tell stories. We're here to do science. So if I'm telling you the history of geometry incorrectly, I'll be glad to be corrected later. Perhaps Mickey will do this. He's good in correcting things, as we just heard. So if you think about it, until the 19th century, the belief was that Euclidean geometry is the geometry of the world. And I think we all Israelis here, I think, had at home the Hebrew Encyclopedia. We all grew on this. And when I read about Gauss as a little kid and with glowing eyes, he discovered hyperbolic geometry, but he didn't publish it because he was afraid to be ridiculed. Anyway, in the 19th century, non-Euclidean geometry emerged. Then mostly things, when people try to express complicated geometries and so on, they usually go to Riemannian manifolds, Riemannian geometry, and then that has remained the case since then. But I think it's really time. So I think perhaps I'm already old enough not to be worried about being ridiculed. I think the next step is really to do geometry on discrete objects. Now I'm with so many physicists around, I only dare to throw this idea into perhaps that would have a major effect on basic questions in physics. If you really think of the world as being discrete in nature, and you develop the corresponding geometry, so I know that such words were said. I'm not the first one to be saying them, but I don't think that this has been, I don't know that this has been seriously pursued. Now, in fact, discrete mathematicians, theoretical sciences, have actually been involved in this business for some time. It's not, but I think we should pose this as a major challenge and something we really try to do. So, for example, expander graphs, if you think about it, expansion is really just the discrete version of the Greek isoperimetric problem. So we have been doing quite a lot in this direction. There are questions about the whole area, which was very popular in the 90s, of mapping metric spaces into each other with small distortion and so on, and so on and so forth. But really, most computer scientists, if you ask them about these questions, we learned all of this in first year computer science, right? In data structures or whatever. What is it that, so it's really good that this is a mixed audience. I'll try to make myself accessible to everyone and tell everyone stuff that they find interesting and perhaps they didn't know this. But one of the things that really every computer science. Let me just do everything that I'll tell that is our own is joint work with Daniel Sisma, a PhD student, and some of it is also with Maria Chudnovsky. I'll come to this. But there is a saying in the Talmud that if you give proper reference, you save the world. So how are we going to miss out on this? So these people are working. So what do you learn in this data structure class or algorithms class? And these are very, very, very practical algorithms. This is places where theory really translates into the real world immediately. So what's the situation? You have a graph, vertices and edges, and there is some weight function on the edges, which you think of as length. So if maps or ways takes you from A to B, what does it do? It find shortest path. I give you two vertices, you look at all, and I'm not talking about how to do this efficiently. This is what you learn in how to do this efficiently is what they teach you in a data structure class. Given two vertices, find me the shortest path. So among all the paths that connect these two vertices, find the one where the sum of w's is as small as possible. And then there is Bellman-Ford and Dijkstra. Every student learns this. But you'll see in a minute that even around here, there are very basic questions that we don't understand. So questions, if you want, that I don't know, Bellman and Ford in the 50s could have asked themselves, but they didn't because the spirit of what it is that you're asking was different then. So here is, I'm telling you now a question that I haven't seriously thought about, but this illustrates the kind of things that even such basic objects really, we still don't understand it. So let's say that W1, W2 are in the same equivalence class if they produce the same path system. So there are two things that I want to say here. Undergraduates who learn this have to deal with what do you do if there is equality. For me, today, there is no cases of equality. Breaking ties is an interesting question, but I want to assume, I'm not going to deal with anything but with generic W's, so there is no equality. Okay, so there is no tie breaking. This issue is not going to be discussed. Again, not because it's uninteresting, because this is not what we're talking about here. So this is really the main object about which I want to talk. If you want, we're developing here geodesic geometry on graphs. So a path system is, you give me a graph, and P is just a collection of PUV over all pairs of vertices. It gives to any two vertices the chosen path between them. So this is the main thing about which we're going to talk. So you understand what it means that two W's produce the same path system. How to study this? The most obvious things. How many equivalence classes? So if you think about it, you'll see this in a minute, that there is a certain polytope. So this equivalence class, let's say you restrict this to bound it from above by one, doesn't matter, by a million, whatever you like. So such an equivalence class is a polytope. It's a partition of the space. What do these polytopes look like? How do you sample them? No idea. I think these are very interesting questions. Stuff that in principle in the second class of data structure you learn. We know nothing about this. But this is not, this is just to give you a sense of how very, very basic questions in this domain, trying to develop geometry on graphs or on discrete, it really leads to very fundamental questions that we don't know. So what is it that I've done with Daniel and later with Maria? Okay, so one property that such a path system has is consistency. So a consistent path system, if it's closed under subpath, which means if I go from x to y, if this is pxy, the chosen path between x and y, and on the way I visit u and v, then this part of the pxy path is puv. This is consistency. So the question at which we started, Daniel and I, is a question. Does every consistent path system say this, is every consistent path system metrical? Which means, is there behind the scenes somehow, I give you a consistent path, is there a W that would generate this? So the answer is a resounding no. So let me first show you the first example that we found, but later we found out that not only it's resounding because this is the rule rather than the exception. So let me first draw an example to you. One thing the first thing that they teach you as a starting graph theorist, always check on the Petersen graph. This is, and in fact, this is a true story. I was once probably visiting here, and I sat in a cafe in San Francisco working, and as usual, or as often, drawing this, and somebody came up to me and asked if I was involved in black magic. The answer is yes, but I didn't reveal. So there are lots of special things about it. It's really fascinating object, mathematical object. But let me tell you two properties of this that will help me explain. So this graph has diameter 2 and girth 5. Diameter 2, you understand. Girth 5 means the shortest cycle in this graph has length 5, which for us means two things. Every two vertices either have an edge between them, or there is a unique path of length 2 that connects them. So the most obvious thing, if you're not trying to be too clever and come up with new things, well, if you have two vertices, your neighbors go by the edge. Your non-neighbors go by the path of length 2. And this is what I do the most of the time, but not always. Rather, this guy, when I want to connect them, I could have gone like this, right? But this is what I do. So just to stress, I take the red path rather than the green path. And moreover, this has a 5-fold symmetry, as you can see. So take all the 5 copies like this. So most pairs, there are 10 choose 2 pairs to connect here. All of them I do the obvious way, except for these 5 pairs. Okay, so it's very easy to check that this path system is consistent, but now let me show you that it's not metrical. It's not metrical because let's suppose that it is. So there is, there is some length to the edges. And the fact that I prefer to go like this and not like this means that x1 plus x2 plus x3 is less. Had it been, so I'm now saying, okay, let's suppose it is metrical. So you get this inequality, and you get lots of other inequalities like this. But when you add them all up, you find out that all these guys are are less than or equal to 0. So that's the end of the proof. So this is non-metrical. So in the first paper with Daniel, or when we started to prove this, I'll make a correct but inaccurate statement, which later I'm going to give you an accurate statement which is stronger than this. This is in the more recent work with Maria. So theorem, most in a very strong sense, graphs. You see this, or this is too low? No? Okay. So an inaccurate statement of our first discovery. So this is with Daniel. Most graphs are non-metrizable. Meaning exactly as Avi says, for most graphs, I'm not telling you at the moment what most graph is, but it's in a very strong sense. In most graphs, this example that we saw here for the Petersen, you can find it there too. There is a path system which is consistent and is non-metrical. Please, Greg.
So just to understand where these polytopes are really coming from and just what the question is really about, you have the orphant of
Can I suggest something? This was something that I mentioned only at the beginning. This is not the core of the lecture. So let's come back to this at the end. Thank you, sorry. Okay, so in most graphs you can find such a path system that's going to be consistent, but not coming from any system of length on the edges. But it tells you even something more, which is really, it's a revealing thing, that when non-metrizability can be easily verified. Why is that? Exactly like here. There is a system of inequalities, and you prove that this system of inequalities is infeasible. And the tool that you use is LP duality. And actually, this is not, this research has taught me many things about actually stuff that I taught in classes, but I understood perhaps a bit better after encountering them in life. So one of the things that I'll tell you later how this comes into play, we create what we call a zoo. It's a list of under 20 specific graphs, like something like this, with a path system in it, and proofs that this particular path system in this graph is non-metric. So this is an important ingredient. So the thing that was a revelation for me is that we found these graphs on the computer. And I don't know if we would have enough energy to sit down and search them from. This was crucial. However, to prove that these are, to get a proof that these examples are non-metrizable, eventually you get a system of inequalities, which you can check, you add them all up, and you get something like here, and that's it. So non-metrizability is relatively, we understand it better than metrizability for a long time remained mysterious to us. So with Daniel, we could prove, on the other hand, and that's a neat proof. If you want to think about it, I don't think you'll find a proof in a few minutes, but if you think about it for a couple of days, I think you'll prove it. It's not a difficult theorem, but it's very pretty. Cycles are metrizable. If you take any consistent path system on the cycle, there are numbers that will give you that. So, but really proving that something is metrizable is still not a problem that we completely understood. So again, one of the things that Daniel and I did, we proved deciding metrizability is in P. This is a correct statement, but it's a lie, in the sense that it's a proof that such an algorithm exists, but I have no idea what this algorithm looks like. Okay. So for those of you who are familiar with the forbidden minor theory and so on, let me add another important ingredient in this whole thing. So metrizable graphs are not minor closed. But are closed under topological minor. Which means if you, when do I say that H is a topological minor of G, there is a subgraph of G, which is H, at which some edges are replaced by paths. Okay. Good. So one of the things that we still hope together with Daniel and Maria to return to, so challenge. And an honestly efficient algorithm. So we know it's in P, but we don't really have an honest algorithm. And
again, I didn't get it. How can you have an efficient algorithm?
So I don't want to get into this because this is probably even less known. And the minor closed theorem, the big theorem of Robertson and Seymour gives you efficient algorithm for various things, but it's efficient really in theory. And sometimes, so this is the kind of algorithm. So let me say one more word about this.
Because the polynomial is very large, that's what you mean.
No, this is not the issue. There is a finite, we can prove that there is a finite list of graphs, which you can check and know the answer. But other than this list is finite, I know nothing about this. Okay, so this is still a challenge. And I don't know if please.
Just
Greg.
exactly on the point.
Okay.
To stay right here.
Yes.
There's the big Robertson Seymour theorem says that you have an Noetherian property, so that anything closed under certain operations is finitely generated.
But that's not true. That's not true for this is true for minors, but not for topological minors.
So you
But we have additional properties that in our case, so in the type of graphs that we are talking, this is a family closed under topological minor that has only a finite list of obstructions.
You need a variation of you
Right.
You might have
No, I cannot use
a corollary of Robertson Seymour.
No, it's not a corollary of there are subsequent theories that people develop, and when you look at what they do, they cannot guarantee a finite list always, but under certain conditions the list is going to be finite, and luckily we are in that. Okay. So again, I'm trying to give you the sense that okay, let me first I'll come back to this. So let me tell you the main theorem that we have together with Daniel and Maria. That's very concrete, and that's stronger than this theorem. So I'm telling you now a better result. So theorem So this is Sisma, Chudnovsky, no, Chudnovsky, Sisma, and myself, sorry. Every metrizable graph that's too connected, I'll say something about this in a minute. With 11 vertices or more is outer planar. So let's go through this word by word. And so metrizable graph, you understand. In general, this whole theory is only interesting for two connected graphs. I mean, if you have a graph that looks something like this, then really you are dealing with each part separately, and to go from here to here and just go to. So two connectivity is really not a restriction. Outer planar means that it's a graph that you can draw in a plane in such a way that all the vertices are on the outer face. So it's one of those guys plus one additional vertex. So you can remove a vertex and remain with an outer planar graph. So this is getting close to where we want to get, but still, so just to give you a sense that we don't really have why this is still a challenge for us, is that, for example, these graphs are called theta graphs, and we can prove that if these, so there are just these three numbers, how long this, and this is, A, B, and C are fairly big and not big, really not big, then it's non-metrizable. If they're very small, they're metrizable, but there's a range in the middle that we don't know the answer. This is it. So doing these things, okay, so let me explain, for example, one question that we are now dealing with. So I want to come back to these questions that I asked at the beginning, about the data structure class, etc. Please do.
Where do you see the applications of?
I don't see applications at the moment. No, serious. Honestly, I don't. I really think we are, creating the foundations for geometry in the discrete world. What did the Babylonians do? What did the Greeks do when they, why would they try to understand the relation between the edges of a right-angled triangle? Why do they do it? Or
What I'm asking, not using the forbidden word application, is really what is for you the meaning of the geometry in the discrete world? What would be what would be connected to it, or what would be?
Okay, so that's a very good question, and the easy thing, the relatively easy thing to do, is to look at geometry and say, does this have other similar phenomena and structures and so on in the discrete world? So there is a whole notion of geodesic geometry, right? Spaces in which you know how to connect any two points. So if you want, this is the idea of, that's what we called our first paper. And where this is going, I don't know, again, if you asked Euclid where this was going to go, I don't know if you would know to, Gauss perhaps had a better idea, but as I said, he was too shy to so I'm trying not to be too shy. Okay, so, so questions like I asked before, and to which Greg referred previously, I had to skip, unfortunately, it's very interesting, but I had to skip, is I can ask the same question now. So we know they're all over the place, but I honestly, so this is a challenge. how to generate. This is at the moment chutzpah to even ask this, but I mentioned it, at least for the record, a non-metrical consistent path system. This is something that Daniel and I these days are thinking about the whole time, and honestly, it seems very difficult. So I'll tell you one, really, I'm really trying to bring you into my workshop and show you the kind of things that I'm thinking about, or we are thinking about. So one suggestion that I gave to him, which seemed very nice and appealing when we started, is to say, okay, let's do weights, but allow also negative weights. Again, you can find out the shortest path also when there are negative weights. And there are questions there which I'm not even going to draw you into. And then, if it's consistent, great. So we answered this challenge. And if not, let's try to move the negatives a little bit towards at some point, something will happen. You'll get a consistent path system. If it's all positive, then no success, try again. But actually, I don't know at the moment of a single example where this works. So any consistent path system from weights, some of which are negative, so far we've been able to recreate also with positive weights. Is this because we're not smart enough, we haven't tried enough cases, or is this really reflecting a mathematical truth? I don't know. So I have no idea about the time. Oh, great. Okay, so I'm fine. I didn't know if we started late. 3. Okay, good. So I'll good. Okay, so I want to tell you just the main ingredients in proving this theorem, which for the moment it's more or less the main thing that we do. So some of them we already went through. So the zoo is a crucial thing. So the easiest thing and this fact. So for example, if I can show that under some conditions your graph is a bit large with with a significant number of edges, then it must contain one of these guys, even as a subgraph or at least as a topological minor. So the zoo is crucial. And then we have this theorem, and this was a good reason to enjoy the partnership of Maria Chudnovsky, who's one of the big people in structural graph theory. Structural graph theory is really like, you had a slide like this. You're really hammering stone with stone in the hope of. So I'll just quote one lemma from the 60s by Lovas, which gives you a sense of what tools of structural graph theory we're using. It's very easy to state. It's really illustrate. It's not particularly crucial or anything, but just gives you a sense of what kind of theorems, what are the tools that people use in structural graph theory. So lemma. So this is just to give you a flavor. Lemma of Lovas. 60s, I think 65 or so. So something like this. If a two-connected graph is all vertex degrees at least 3, so there is no degrees of vertices of degree 1 and 2, and has no 2 disjoint cycles, then G is one of 3 things. G is K5, or a wheel, that's a wheel, or K3n plus. So there is 3, there is n here, everyone to everyone, and you add some edges. This is the kind of, and this is, for example, a typical main step in what we do. So we ask, if there are 2 disjoint cycles, then we can find animals from the zoo. There is none, then the structure is very limited. So that's very typical of work in structural geometry. And there's a lot of this sort there. And I think with this, I should stop. Thank you. Please, Tal.
So you said that you don't have an application, but you have some intuition or something of why maybe this could be used further, not just in the theoretical sense that it's interested in looking at so on.
You know, this is really done as foundational work. You know, I was really shocked to discover that this question that Bellman and Ford could have asked themselves in the 50s, there seems to be really no information about this. I would like to understand, you know, what this is like. What is possible? It is very elementary thing that you teach in a data structure. So it's very foundational. I don't have it. I don't do this with some, you know, not applications, not. It seems to me very foundational. I would like to understand this. You know, I don't know what Riemann would have told you if you asked him. You know, these surfaces that have Riemann that you're talking about. What good are they? Well, they're very good, even if he didn't know.
Great. Well, thank you. So we should stop for lunch.
Yes.
And resume at
We have to change the
2
timing.
o'clock.
Wait, no, much later than 2,
What?
because we're running very late already.
No, it's
It's okay.
fine.
Okay. So see everyone.